Hello student, I am Vishwanath. Welcome to my YouTube channel. Today at first I am going to show an interesting experiment. This is a simple instrument which has no battery or no cell. That is no electric source. It is only a simple wheel. Okay. And now if I rotate this wheel, then some electricity is produced. Okay. When I stop the rotation, then the electricity also stops. Okay. Therefore this instrument produces electricity from or electric energy from mechanical energy. Okay. This instrument produces electric energy from mechanical energy. Here we are doing some work by rotation of this wheel, and therefore the light glows. Okay, due to passing of the current. This current is known as induced current, and this EMF is known as induced EMF. So today I am going to discuss about induced EMF and induced current and Michael Faraday's laws about electromagnetic induction. Okay, let's watch the video. This is a closed coil linked with a galvanometer, and there is no battery or electric source connect with this closed circuit or closed loop. Now a powerful bar magnet is introduced near to the coil. When this bar magnet is moved towards the coil, then the pointer of the galvanometer is deflected. Okay. When the movement is very fast, then the deflection of the pointer of the galvanometer is also high. Okay. When the movement of the bar magnet is stopped, then the pointer is also moved to the initial position or zero position. That's why you can say that when a bar magnet or magnetic field is changed near to the closed coil, then an electric current or electric EMF is induced inside the coil. Okay. And when the direction of the bar magnet is opposite, that is when the bar magnet is moved away from the coil, then the current also generated in this coil, but the direction of the flow of current is reversed. That is, the deflection of the pointer of the galvanometer is also become opposite to the initial one. Okay. That's why you can say that when the movement or direction of the change of magnetic flux inside the coil is reversed, then the flow of current or direction of the induced EMF is also reversed. This phenomena is known as electromagnetic induction. And this current is known as induced current, and this EMF is known as induced EMF. Okay. From this experiment, Michael Faraday stated two laws. And these laws are known as laws of induced EMF or laws of electromagnetic induction given by Michael Faraday. Okay. Let's see the laws. Faraday's first law: when the linked magnetic flux phi with a closed coil changes with time, then an induced EMF is generated inside the coil. Okay. Second law, the magnitude of induced EMF is directly proportional to the rate of change of magnetic flux linked with the coil. Okay, that is, if we denote the induced EMF by epsilon and the linked magnetic flux by phi, then epsilon is directly proportional to d phi dt. These two laws are known as Faraday's law about electromagnetic induction. Next, Lenz law. Lenz law states about the direction of induced magnetic field or induced EMF. Lynch states the direction of induced EMF. Lynch law states that the direction of induced EMF is such that it always tries to oppose the cause of change of linked magnetic flux with the coil. That is, the direction of induced EMF is such that it always tries to oppose the movement of the bar magnet. Okay. Therefore, from Lenz law, we can write that epsilon is proportional to minus d phi dt. Here, minus or negative sign indicates the opposing force. Okay. That's why we can write that epsilon is equal to minus n d phi dt. Here, n is the number of turns of the coil. This is the n is the number of turns of the coil. Let us explain the Lenz law. If we consider the bar magnet is moved towards the coil, then the EMF is produced such that the near point of the coil is induced by north pole and the away point is induced by south pole. That's why current moves through this direction, that is in clockwise direction. Okay, clockwise direction. That's why the north pole here repels north pole. Therefore, this north pole opposes the movement of the bar magnet. Okay. Now, when we move the bar magnet away from the coil, then the direction of the current will be reversed. Okay. That is, the direction of the current will be reversed. That is, in this case, here south pole is induced near to the magnet and away point north pole is induced inside the coil. That's why the south pole here, south pole attracts the north pole of the magnet. Therefore, this south pole, induced south pole, opposes the movement of the magnet. Okay. This is known as the Lynch law. This is a plate having area capital A. A is the area vector of this plate. The blue color denotes the magnetic lines of force of the magnetic field passing through the plate. B is the magnetic field strength or magnetic field at this place. Now, magnetic flux phi is equal to A vector dot B vector, or phi is equal to AB cos theta, where theta is the angle between A vector and B vector. The magnetic flux denotes the magnetic lines of force passing through the area in normal direction. Okay, this is known as magnetic flux. That's why we can also write the Lenz law or Michael Faraday law in the following way. Epsilon is equal to minus n derivative of AB cos theta with respect to t. Okay, this is another form of Lynch law. or expression of induced EMF. We can also prove Lenz law by the principle of conservation of energy. Okay. At first, let us assume that the Lenz law would be wrong. Okay. Therefore, when we move the bar magnet away from the coil, then the induced pole of inside the coil or solenoid will be north and south, opposite to the Lynch law. That's why this north pole repel north pole. Therefore, the bar magnet moves away without any work done due to the repulsive force between two north poles. That's why we can get huge electric energy without any external work done. But it violates the principle of conservation of energy. Okay. On the other hand, when we bring the bar magnet towards the coil, then the induced EMF is such that the near point would be south pole and the away pole, away induced pole will be north pole, which is the opposite to the Lynch law. Therefore, this induced south pole attracts the north pole. That's why the bar magnet moves itself towards the coil without any external work done. Therefore, we also get the huge energy without any doing external work. This violates the principle of conservation of energy. That's why Lenz law is true. Okay. Lenz law supports the principle of conservation of energy. Now I am going to discuss about the induced EMF inside a moving coil through a uniform magnetic field. Let us consider PQ is a straight wire connected with a galvanometer G, and this is a closed circuit. Okay, this wire PQ moves inside a uniform magnetic field B. Here the velocity or movement of the magnetic field, movement of the wire B is normal to the magnetic field B vector. Here V is the velocity of the wire, and here the angle between B and V is 90 degree. That is, the velocity vector and the magnetic field vector are normal to each other. This coil covers a distance x in time t. That is, displacement of the wire is x in time t. Therefore, during time t, it produces an area PQRS. PQRS. The area PQRS, that is A is equal to area A is equal to PQRS. This is equal to x into L. This is equal to x into L. Here PQ is equal to L and QR is equal to x. That is L into x. Okay. Therefore, the change in magnetic flux d phi is equal to A into B. A into B, that is change in area into magnetic field. Okay. The rate of change of magnetic flux d phi dt is equal to d of dt AB. Here the direction direction of A vector and B vector are parallel to each other. That is, angle between A and B is 0. Therefore cos 0 is equal to 1. Now putting the value of A x into L, we have derivative of t with derivative of Lxb with respect to t. Okay, d phi dt is equal to derivative of Lxb with respect to t. Here L and B are constant, and we have L into B into dx dt. Here dx dt is equal to v, is the velocity of the wire. Okay. Therefore, induced EMF inside the wire is epsilon is equal to mod of n d phi dt. Here we neglect the negative sign. Also, only consider the magnitude of the induced EMF. Okay. Therefore, we can write induced EMF epsilon is equal to NBVL. Here, N is the number of turns on the wire. If there is single wire, then N is equal to 1. If theta be the angle between B vector and V vector, then epsilon is equal to NBVL cos theta. Okay. From this law, we can also find out the potential difference or EMF, induced EMF generated between the two wings of an aeroplane. When an aeroplane moves through the Earth magnetic field, then an induced EMF is generated between the two wings of this aeroplane, and the magnitude of the induced EMF can be find out from this formula. Okay. Now we consider a wire is placed inside a uniform magnetic field B, and the wire rotates with an angular speed omega in a circular path. OP is the length of the wire, it is equal to small r, and the one point of the wire is fixed at the center of the circle. Therefore, this wire is rotates in this way. Okay. Therefore, an induced EMF is generated inside the wire. Let d theta be the angular displacement of the wire during time dt. Okay. Therefore, we can write the angular speed of the wire omega is equal to d theta dt. That is, omega is equal to d theta dt. Now, the changing area during time dt is Ga is equal to half into OP into OPQ. Okay. This is equal to half into R into d theta is equal to, that is dA is equal to half into half R square d theta. Now the magnitude of induced EMF epsilon is equal to d phi dt. This is equal to half into R square d theta dt. Since here R is constant, okay, R is constant, therefore epsilon is equal to half R square d theta dt. This is equal to epsilon is equal to half R square omega. This is the magnitude of the induced EMF inside the wire. I am going to finish my discussion for today. I shall meet you again in my next video, and thank you for watching my video. Thanks a lot. Have a nice day.